Exercise number 8 is a little more complex. We are asked to evaluate the line integral along c of x squared dx plus y squared dy, where c consists of the arc of the circle x squared plus y squared equals 4 from 2, 0 to 0, 2, followed by the line segment from 0, 2 to negative 1, 1. There's a whole lot of stuff there. Let's start by unpacking what c is. In the current edition of the textbook, rather than describing C, they just draw a picture. But in previous editions, this was described in words. And in problems that we write, such as on exams, they tend to be described in words. So you want to make sure that you construct the thing from what we're given. A picture might help, or it might not, depending on how you think. But just in case, let's go ahead and sketch a rough little diagram here. C consists of the arc of the circle, x squared plus y squared equals 4, so that is a central circle of radius 2, from 2, 0 to 0, 2. So we have these points. We have a point at 2, 0, and we have a point at 0, 2, and there is the arc of the circle connecting those. I'll draw a little arrow here because it is going from 2, 0 to 0, 2. The order matters. Followed by the line segment from 0, 2 to negative 1, negative 1. Something like that. Let's see if I can get the, I guess that'll be about there, give or take. Something like that. Sure. Here we'll have negative 1, sorry, negative 1, 1. I believe I misspoke there. You can see what's there, negative 1, 1. And I'll draw a little arrow there to indicate the direction we're going here. And all of this together is the curve C. So, the first thing to note here is that this curve is only piecewise smooth. There are two natural pieces that it occurs in. When we have a sharp corner like that, we're usually going to have difficulty coming up with a single parameterization to describe the whole thing. It would basically be a piecewise function if we did. So we can instead split this up into two pieces, C1 and C2. And the line integral along the curve C would be equal to that integral along the curve C1 plus the integral along the curve C2. We often say, even though C is a path, it's not a number, the notation that we often use for something like this is C is equal to C1 plus C2. Again, these aren't numbers, we aren't literally adding these, but this is a common little shorthand to indicate this. So we can evaluate two separate integrals, one for the arc, one for the line segment, and then add the values of those at the end. In order to do anything with these are integrals in terms of x and y, so we need parameterization in terms of some parameter like t. For the first part, for C1, we see that this is, again, this is an arc of a circle. Its radius is 2, so we expect to use things like 2 cosine, twice the cosine of something and twice the sine of something. We're starting here on the x-axis and moving upward in this counterclockwise direction, which means that it would be natural to use the usual parameterization where cosine is associated with x and sine is associated with y. But again, since our radius is 2, we want to have 2 cosine t. Y equals 2 sine t, where t runs from, now here we're kind of thinking of t as like an angle, so the natural sequence for t would be from 0, where we're starting, up to pi over 2, where we end. Think back to chapter 13, or further back to Calc 2, chapter 10, I believe it was, when you would have worked with parametric equations. Let's, if you want, you can do a quick check to make sure this is starting and ending in the right places. When t is 0, you have 1 and 0, so you have 2, 0, and 2, 0 is the point in question. When t is pi over 2, you get 0 there and 1 there, so you have 0, 2, and 0, 2 is where we end. So it's at least starting and ending at the right points. This looks pretty good. Right. So there is our C1. So the integral that I'm going to call I sub 1, I1 will be the integral along the curve C1 of x squared dx plus y squared dy. Now remember from the textbook, this is a shorthand notation for the sum of these two separate integrals. It's the integral along C1 of x squared dx plus the integral along C1 of y squared dy. It's common, however, to just abbreviate these like this. This would be very rigorous symbolically if we put in grouping symbols, because the integral sign is treated like a summation. So this is basically summing x squared dx plus y squared dy, and then this actually would work out fine if you think about what this would mean in terms of Riemann sums, and that would work out great. But we don't usually write parentheses there. I'm not certain why. I don't know, but I suspect that this notation is probably due to physicists rather than mathematicians, and we've just sort of picked it up. But there's really no telling. That's entirely speculation on my part. At any rate, we have this integral of all of this stuff, which would conceptually be two separate integrals, except we're about to change everything to be in terms of t, so we may as well just treat it as one. Okay? So let's just go ahead and start substituting in what we have. We're integrating along the curve C1 and writing everything in terms of t. T goes from 0 to pi over 2. So this would be the integral from 0 to pi over 2. We have x. What is x? X is 2 cosine t squared. X squared dx. What is dx? Well, if x is 2 cosine t, then dx is the derivative of that dt. Right? Derivative of cosine is negative sine. So we have negative 2 sine t dt. This is x squared dx plus, I think I might run out of room, so let's move this down here, plus y. Y is 2 sine t squared dy. Well, what's dy? That'll be a 2 cosine t dt. So you'll note that I wasn't relying on the formulas that were presented in the textbook, although those work. If you'd like, you can certainly use those. The notations are a bit extensive. I'm just saying, we have expressions for x and y. We can plug those in. We know how to find differentials. We evaluate those differentials. We just plug in the things that we know. And there we go. The notation of this is not created out of thin air. The notation tells you exactly what the structure is. Use that, plug things in where they go, and it'll all work out just fine. You'll want to, of course, clean this up a little bit, where we would have this first term, we'd have, looks like negative 8 cosine squared t sine t, and there's a dt, but I'm going to factor that out because I have that in both factors here. So we have plus 8 sine squared t, almost forgot cosine t, there we go. So we have that dt. You see I've factored out the dt from these two terms. Now what I've written here is, literally just a Calc 1 style integral, right? You can probably factor out the 8, maybe split these up if you wanted to. Each term involves its own substitution, so if you're not comfortable doing that mentally and you want to write out the substitution, you probably want to split that as two integrals. Leave that to you to work out, but you should get 0 for that one in the end. I might talk briefly at the end about why that's 0, but confirm that you can get 0. But this is not the answer, because if we follow this chain of equality back, this is just I1. We need I2, a second curve. C2 goes from 0, 2 to negative 1, 1. So let me jot that down here. We're going from 0, 2 to negative 1, 1. So our curve C2 would be a parameterization for this line segment. So let's think about this. X starts at 0 and decreases by 1. So that would be a negative t. Y starts at 2 and also decreases by 1, so that's a negative t, as t goes from 0 to 1. I just used the standard methods, the shortcuts for building a line segment from back in section 12.5. Everything we've done in this course is kind of coming together in chapter 6. So we have that. So we have the integral, the second integral is the integral along C2 of, what did we have? Was it x squared dx plus y squared dy? Yes. X squared dx plus y squared dy. So that is the integral along C2. Now t is going from 0 to 1. We have x squared dx plus y squared dy. X is negative t squared. Dx is negative dt. Y is 2 minus t squared. Dy is negative dt. So the integral from 0 to 1 of, looks like negative t squared plus, well, let's make that minus 2 minus t squared dt. And now this doesn't even need substitution. This is just a polynomial, one of the easier types of integrals. You can just expand that out, collect like terms, cancel things in common, blah, blah, blah. And that should work out to negative 8/3 if I have, nope. No, yeah, that's the right one, sorry. Thought for a moment I was looking at the wrong part of my notes, but that is it. We have negative 8/3 there. So the total integral, the whole integral along C of x squared dx plus y squared dy would be the first integral plus the second integral, because C is C1 plus C2, so the integral is I1 plus I2. You don't have to call these I1 and I2, I just did it for a shorthand notation just to give them names. I1 we found to be 0, I2 was negative 8/3, so we get a total of negative 8/3. You might wonder if this even makes any sense. What is this describing? How big is this number? So let's come back up here and look at what we have. On the first leg, we've got x squared dx plus y squared dy. Those are the same structures, just different variables. And there's a lot of symmetry in this problem we have, right? Every xy pair kind of appears in its value and also reversed as we move along this arc of the circle. So the first part, x squared dx, we're starting at an x of 2 and steadily dropping toward 0. For y squared dy, we're starting at a y value of 0 and steadily increasing to 2. They're at the same rates but opposite directions, right? The beginning of this path is basically the end of that path, except in the opposite direction. So with all of that in mind, in hindsight, it makes sense why this sum would be 0. Because we have x values that are dropping, we have y values that are x values that are decreasing, y values that are increasing, and those just basically balance each other out. the x squared and y squared will be equal in values at various points, but dx will be negative because as we move from this point to this point, x is decreasing. dy will be positive. So that sum, it makes sense why it would be 0. It's a little tricky to reason through that ahead of time. I wouldn't recommend just guessing at that because some weird stuff can happen. But in this particular case, that worked out fine, so that makes some sense. As far as what these values are, well, we can think about, as we go from this point to this point, we've got x squared. X starts at 0 and moves to -1. So x squared goes from 0 to +1. But it's usually a good bit less than 1, right? The average value of it would be, well, actually about a third, but averaging is based on integrals. But if you just made a naive assumption and said, okay, well, a half is halfway through, and a half squared is a fourth, so let's say it's around a fourth, give or take. It's a very crude estimate, but ballpark. Y values start at 2 and drop down to 1. So to get y squared, you could do a similar very crude estimate. Halfway between is about 3 halves. Square that, you get 9 fourths. You can add that other fourth, we get 10 fourths. That's what 5 has, about 2.5. So with extremely crude estimates, we would think that those would add up to about 2.5. Each one is moving a distance of 1. And 8/3, what we found here, ignoring the negative, 8/3, that's 2 2/3, which is a little over 2.5. So that is in the rough ballpark, right? We were making very crude estimates. This is about the right size. As to why it's negative, well, if we look at these things, x squared and y squared are always positive, but moving from 0, 2 to -1, 1, dx is negative, x keeps decreasing. dy is also negative, y keeps decreasing. So these values that we found are being multiplied by negative step sizes. So that total comes out to be negative instead of positive. If we were to integrate from -1, 1 up to 0, 2, then we would get the exact opposite value. That would give us positive 8/3. But we're working against them, so it's negative. Again, the direction matters here. If you're just integrating with respect to arc length, that differential ds is always positive, no matter which direction you're going. So switching direction doesn't really change anything. You're just integrating with respect to the length of the arc. But with a dx or a dy, the direction of movement actually matters. So if you reverse the direction of your path, you will negate the value of the integral. But yeah, so this is a much more complicated problem than number 2. But still, we didn't really have to use the formulas in the book, right? It was just, again, as long as you come up with a parameterization, remember how differentials work, you just use what it's asking you for, plug those things in, simplify algebraically, evaluate your integral using Calc 1, maybe early Calc 2 techniques. That's about all there is to it. So nothing too bad there.